Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the adiabatic saturation and wet bulb temperature. Firstly, let's talk about the adiabatic saturation process. Relative humidity and specific humidity are frequently used in engineering and atmospheric sciences, and it is desirable to relate them to easily measurable quantities such as temperature and pressure. One way of determining the relative humidity is to determine the dew point temperature of air, as discussed before. Knowing the dew point temperature, we can determine the vapor pressure PV and thus the relative humidity. This approach is simple but not quite practical. Another way of determining the absolute or relative humidity is related to an adiabatic saturation process shown schematically and on a TS diagram. The system consists of a long insulated channel that contains a pool of water, a steady stream of unsaturated air that has a specific humidity of omega-1 and a temperature of T1 is passed through this channel. As the air flows over the water, some water evaporates and mixes with the air stream. The moisture content of air increases during this process, and its temperature decreases. Since part of the latent heat of vaporization of the water that evaporates comes from the air, if the channel is long enough, the air stream exits at saturated air and temperature T2, which is called the adiabatic saturation temperature. If makeup water is supplied to the channel at the rate of evaporation at temperature T2, the adiabatic saturation process described above can be analyzed as a steady flow process. The process involves no heat or work interactions, and the kinetic and potential energy changes can be neglected. The conservation of mass and conservation of energy relations for this two-unit, one-exit steady flow system reduce to the following. The mass balance of this system is 1. The mass flow rate of dry air remains constant. 2. The mass flow rate of vapor in the air increases by an amount equal to the rate of evaporation. The energy balance of this system is. From energy balance, we have the specific humidity and the unit, and the exit phi2 equals 100%. Then we have the specific humidity omega-2. The specific humidity of air can be determined from these equations by measuring the pressure and temperature of air at the inlet and the exit of an adiabatic centrifuge. Now, let's talk about the wet bulb temperatures. The adiabatic centrifugation process discussed above provides a means of determining the absolute or relative humidity of air, but it requires a long channel or a spray mechanism to achieve saturation conditions at the exit. A more practical approach is to use a thermometer whose bulb is covered with a cotton wick saturated with water and to blow air over the wick as shown in Figure 7.6. The temperature measured in this manner is called the wet bulb temperature, TWB, and it is commonly used in air conditioning applications. The basic principle involved is similar to that in adiabatic centrifugation. When unsaturated air passes over the wet wick, some of the water in the wick evaporates. As a result, the temperature of the water drops, creating a temperature difference between the air and the water. After a while, the heat loss from the water by evaporation equals the heat gain from the air, and the water temperature stabilized. The thermometer reading at this point is the wet bulb temperature. A device that works on this principle is called a sling psychrometer. Usually, a dry bulb thermometer is also mounted on the frame of this device so that both the wet and dry bulb temperatures can be read simultaneously. In general, the adiabatic saturation temperature and the wet bulb temperature are largely the same. However, if air, water vapor mixtures and atmospheric pressure, the wet bulb temperature happens to be approximately equal to the adiabatic saturation temperature. Okay, that's all for this task. Thank you very much and see you next time.